Hello, everyone. Good morning. I wish you a very warm welcome to the Fall CAE seminar series. Our first speaker is Professor Islam Mantavi, who is an assistant professor at Rowan University, and he is going to talk about advanced manufacturing techniques in infrastructure applications. Dr. Mantavi is assistant professor in civil and environmental engineering at Henry M. Rowan College of Engineering at Rowan University. He's been there since fall 2022. He's a registered PE in Nevada. His research focuses on concrete additive construction and metal additive manufacturing. In concrete additive construction, his expertise is in areas such as topology optimization, reinforcement techniques, hazard protective systems, functionally graded structures, adaptive and reconfigurable structures, among other topics. He's an associate member of ASC and SCI and a member of ACI, where he contributes to multiple technical sessions. We are very thankful to Dr. Mantavi for taking the time to be with us today, and we look forward to his talk. Dr. Mantavi, the floor is all yours.
Thank you, Bernard, for the introduction, and I hope you can hear me well. So today I'm going to talk about my research at Rowan since I started in 2022, spanning concrete and metal additive manufacturing for infrastructure application. So seminar outline will be like I can introduce the problem and overall view of it, and we're going to talk a little bit about the background on our in general in concrete additive manufacturing or construction. And third one will be introducing my lab, which we call Additive and Robotic Construction Laboratory. And after that, we'll go through three projects. The first project really is bio-inspired friction beams, and second project related to developing bridge column for seismic zones using rocking columns, and the last project is underwater 3D printing for marine infrastructure. And at the end, I will conclude with having an open discussion with you all on how we can envision additive manufacture for larger infrastructure application and how can this technology make a difference. So starting with introduction and conclusion, I always start my presentation with this slide saying like this is an image from 1950 versus 2019, often left on the right. And I always say, what is the difference between these two slides, except from like minor maybe equipment enhancement? The only difference really is, the black or white color. So basically, for long time, we are placing reinforcement casting because we are producing mass members. And the idea here is, can we actually integrate some of those new technology from 3D printing and additive construction to enhance infrastructure responses? Similarly, also in metal side, we also do that the same in the way we make our steel in terms of the large furnaces, etc. So the same image here from 1950 and 21st century showing how we made our steel. I will not focus in this presentation on our research in steel. We almost like 50-50 between steel and concrete at this stage. But in future, if you are interested, we can schedule another presentation on the steel side of additive manufacturing for infrastructure. So background quickly here, if you check ISO ASTM 52,900, you will have the classification of all additive manufacturing technique regardless of materials. So you have sheet lamination, which is basically metal, material extrusion, which is concrete metal polymer, binder jetting, which also suitable for concrete metal and polymer. Material jetting, mainly polymers, powder bed fusion, suitable for both metal and polymers with different techniques. On the right side, you can see the direct metal laser sintering and others. Fat photopolymerization for polymers and direct energy deposition for metals. Our lab focus on the one in concrete extrusion and direct metal laser sintering and exploring other techniques too. So advantage of additive manufacturing in general is theoretically reduction in labor needs, enhanced labor skill set, saving time and reduction of material wastage through optimization, either structurally or topologically optimization, and broaden design creativity and problem solvability, potential reduction in carbon footprint, and on-demand manufacturing, which is really a very interesting benefit from here. Like if you have to print on demand to replace structural component instead of having them in the stock, and creating competitive economy and businesses. So at our lab, we categorize construction now into three bullets here. What is the conventional construction, where we all know about forming, placing reinforcement, and casting. Most of the 3D printing technique we see right now is involving printing partially the structure, so printing formwork, wait until curing, place reinforcement, and casting. We call that hybrid construction because mainly you also cast. Our goal at Rowan is create additive construction technique where the reinforcement is integral part of the process, or creating a structure that is predominantly compression with some redundancy. So just to introduce concrete additive construction in general, as you know, historically concrete requires slump and vibration to fail formwork and encapsulate reinforcement. However, in concrete 3D printing, we actually changing the material, and especially the rheology of the material is altered, so that allowing us to print layer by layer. And that actually induced challenges, especially in the material itself or the structure as a whole. And those challenges include during the print buildability failures because not tuning the material rheology, or early age shrinkage and cracking, because instead of having the cast concrete encapsulated in formwork, now we have an entire structure is exposed to the environment and elements. One big challenge is reinforcement techniques, or how to integrate reinforcement. And for sure, as any 3D printing technique, you will have anisotropic behavior and interlayer bond problems. So introduction to our lab. Our lab, we have 5 students, 4 PhD students working in the lab. Mainly 4 of them are concrete and 1 is steel. And our lab objective is between concrete additive construction and metal additive manufacturing, both having optimization technique, hazard systems. In concrete, we talk about locally sourced material and low carbon footprint, novel reinforcement technique, and also multi-hazard functional structure. In metal, we think a lot about how to repair corroded steels or cracked steel using cold spray repair, and also using hazard protective systems. And as I mentioned, I will not touch metal additive manufacturing in this presentation, just to have a focus. So in general, for our lab, we create a workflow or flow chart here to develop different concrete mixes from mortar to UHPC and others, where we do quick testing on flow table test and setting time to assess quickly the printability of the material. And after that, we do what we call performance-based printing. So basically, after we develop initially the material, we go through extensive testing through the printer with so many different parameters of printing, extrusion rate, building, printing speed, etc., to evaluate the printability of the mixes. After that, we end up with hardware structure that we test for flexion, compression, and others. And we also collaborate with a faculty here, Dr. Trias, with LiDAR scanning to be able to capture the geometry of the structure. After or during and after printing, actually, to capture comparison between as print versus the CAD model. When we fail in any of those, we go back and adjust our binder. But since 2023, we have different versions of those materials, so we actually are now in phase of using those to build structures. So our lab at Rowan, we have the SCARA Elite Roadrunner, and this one is a printer robotic system on a rail. The rail is 14 feet long. The robotic arm has extension of 7 feet, so it can print 7 feet around itself, and height of 7 feet too. It can print 1 to 4 inch per second, and it has 360 rotation, so it can actually rotate around itself completely. And we have two systems, one on the right side, we call it closed system because it's a syringe tube. And the left side is the open system from the mixing to pump to extrusion using the auger system that regulate the extrusion rates. We can print now from 5mm nozzle up to 2-inch nozzles. So here is a comparison between the system we have. So on the left side, on the same material that we developed at Rowan here, using locally sourced material, 20 miles from the university, all the ingredients. You can see the same mix is printed with 3 different systems. One is a tube that involve more of a piston type extrusion, and the middle one is the auger system printing a much bigger cylinder, and the right side is printing out of the pumping system that we have right to the nozzle. And you can notice also that there is someone moving around with a LiDAR to scan the structure as we are building it to capture the deformations. So same makes 3 different systems and passed almost all the printability requirement. And also we take a good pride in the quality of our prints. Some of our mixes also include fibers. So we have fibrous mixes for 3D printed concrete. Our mixes range without fiber around 10 KSI as cast. We're gonna drop it a little bit once it's printed, dropped by 20%, so around 7 to 8 KSI without fiber. With fiber, you can increase 2 to 3 KSI, and it actually have benefit in the flexure capacities too. So here is another type of mixes that include steel fibers. In this case, we are able to print fibers from 4.5mm, 6mm, and 12mm, 12.7mm with the fiber actually as integral part of the mix. We also print in slopes. I just wanted to have a disclaimer here. We don't use any accelerant in our mixes. So all our mixes are fresh. If you hit the mix after printing, it will collapse. So you can see here, we print this full pyramid without support using fibrous mix we have, and also we printed without fibers. And the idea here is, can we unleash the potential of 3D printing by printing on such slopes? So this slope is 26 degrees from the vertical position, and we're able to complete the entire structure printed. We also take it one further step and print that for like flare type structure or like flared pier. So basically here, as you can see, with this same fibrous mix, we're able to print any slopes. We take that to what we called stress testing. So we print until failure and to the slope. So as I mentioned, this is 1K, no excellent in the mix, and was failing here by geometry rather than by the material. As you can see, partial collapses on the left side of this pier, and this was around 65 degree slope from the vertical position. And we were able to identify that without fiber, we actually can achieve 45 degree slope. With fiber, we can actually extend that to 65 degree slope. We also work on geopolymer concrete. I'm pretty sure you're familiar with geopolymer concrete that replace cement with pipe product from different industry like fly ash, silica fume, slag, and use chemical activators to create the binder. So we also work on that area, and very challenging material as we do. So it's very flowable, but it has transient change in rheology. So we rely on that changes to start printing, and we're able to print different types. And later on, I will show you in project 3, we use that for 3D printing underwater. So this is concluding the introduction of the lab. So I'm going to start talking about the first project is how to use this material to develop a structure component. So topology optimization is a way to optimize, a method to optimize using an algorithmic model to basically subtract material where it's a low stress region and lay out the material where it's needed, given a set of load condition and constraint. Is very famous in homogeneous material like steel. As you can see here, you can actually achieve the same performance as the right side from the left side by removing material from low stress region. It has been investigated in both 3D printed and non-3D printing application to create lighter structure. You can see one of the bottom side of the screen here, a 3D printed segmental post-tension bridge in Ghent, Belgium, where they 3D print those elements and collect them together and post-tension them. And the analysis here involve topology optimization. So background here on general reinforcement for general casting of concrete. Usually the way we have the reinforcement in our beams, we cast is governed by the formwork. So basically we move from bent bar to straight bars to actually make the construction easy, instead of having also the shear reinforcement in a direction where it's actually resisting the principal tension. We're actually using a vertical stirrups also governed by constructability. So our goal here is, since our current technique actually is governed by the way of construction is formwork, can we actually step back a little bit and think about rethink the way we have the reinforcement technique for 3D printed structures. So we came up with a concept that's really from nature for how bees build their honeycombs. So basically you will have a structure analysis of any beam, you will have tension trajectories and compression trajectory lines, and come up with hybrid technique where 3D printing of those cellular unit or lattice structure, and in process able to include reinforcement. For example, here we use flexible cable reinforcement. And the idea here later on that using the stress trajectory can fill the cells selectively using a flowable material. But the difference between us and the rest is we actually immediately fill it with the same system, which is a 3D printing system, by changing the rheology of the material. So this is just a schematic here. So you can see here we're printing a 3 feet long beam, and manually now the student is placing the cable in tracing the tension line and printing and continuing the printing process. And right after printing, we will be able to change the rheology of the material and make it flowable and selectively fill as needed. For sure, we will have to fill it around the reinforcement to protect from corrosion at the compression line and at shear areas. And larger, bigger beam, you will have more benefit of this technology. However, in a smaller one, we may have really like few cells that is open, that is low stress as region. So as you can see here, we start from layer by layer and incorporate reinforcement. And until we finish, we can also use bent bar and straight bar. I'm going to explain that in a minute. And the idea later on is to start, after you finish, immediately fill those cavity. The caveat here actually is once we print and cast closer to the time, we were surprised that actually they fuse really nicely. There is no cold joints. I actually have one sample here with me that can show you clearly the material was fused nicely. And for the 5 cells you can see here, just because of the geometry, we have a limited benefit of optimization, but in larger elements, you can see the benefits. So one cable, in this cable reinforcement, we took this and we tested, and you can see the DIC systems here. What we noticed from this cable reinforcement, because of the slips that happen to the cable, every time you have a crack formation, you will have a slip of the cable, and after that, you will have the re-engagement. So every value you see on this curve is representative initiation of a new crack. And here is the digital image correlation result of this beam as tested, and you can see basically you can use the first principle of concrete to design this beam easily using rigid reinforcement or flexible reinforcement regardless. because the middle section of the beam is actually supposed to be cracked in normal situations. The only thing the challenging here is controlling the crack width, because the cable here is slipping and increasing the cracks. So we take that to another direction when we start using bend bars. But in this case, we're using different type of reinforcement. So the left beam here, you can see that we used U-bar, but we didn't have any shear reinforcement. And the idea intentionally was to see how those lattice structure can perform and what the shear capacity of this beam. And after that, we came up with a different reinforcement technique where we tried bend bar, and we tried also using welded wire mesh in the shear region, and even district Z-bars, as you can see here. Those Z-bars, actually, because the material has really high bond to the concrete, we actually, the development length is very short, similar to UHPC, so we're able to withstand those shear loading. So as you can see here, one without shear reinforcement on the left side and two shear reinforcement strategies. And here is a process of the first beam, and right after printing and casting, on the left side, you can see the shear capacity of this beam was around 13.5 kips. And a nice failure that combined also shear and flexure. And the middle one is dominantly shear, but it extends because of the load. It was 3-point loading. And the second one was shear reinforcement, which were able to suppress shear cracks using the welded wire mesh. And we shifted from shear failure to flexure cracks and flexure shear cracks. And the last one is using the Z-bar, also have the same conclusion of reinforcing those ends from shear failure and shifting the failure toward the middle of the beam. A lot to be done to optimize and also make sure that those opening has some flexibility and rigidity, and also ductility, so that allow to reduce crack width as we move forward. But this is like more of an approach that I tell my student that don't think conventional way when you do 3D printing. We will not be able to put stirrups in this case. The second project here is related to another idea we have using this technology for seismic region, where basically developing bridge columns that can resist seismic loads. So I'm pretty sure you're familiar with this resilient diagram. On the left side, you can see under a convention element that suffer functionality loss, need time for repair. However, new seismic system always try to reduce functionality loss and downtime to enable functionality and rapid recovery. So as part of my PhD at the University of Nevada, Reno, I was part of a team from University of Washington and University of Nevada, Reno to test rocking columns for seismic zones that actually boast pretension column and has a connection with the foundation using wet socket connection, and the cab using reduced section and hybrid bar type of connection with grouts, and having, as I mentioned, pretension, unbonded, and energy dissipation through unbonded bars and the interfaces. And the idea is simple here, is that instead of make the beam or column rigid and induce flexure behavior, what we're trying to do here is to allow it to rock back and forth. And the pre-stressing will allow it to recenter. The confining tube at the end will confine concrete from spalling, and the rebar inside will actually yield and dissipate energy. So you can combine the moment rotational response from strand and rebar and achieve this nice flag shape that dissipate energy and self-center the column back. So here's me like 12 years ago at University of Nevada, Reno, testing this in a large scale testing, 70 feet long bridge in the lab on 3 shake tables. And as you can see, a lot of deformation, sways. However, everything self-center nicely to the original position without permanent collapses. And the few challenges we have after we finish the testing, everything looks nice, and the inspector will go there, see minimum damage, but the main damage was actually the fracture reinforcement that act as not damper, like energy dissipative devices. So we did a lot of work to identify the damages, but most of the DOT actually criticized the system, saying that we will have no way to repair those columns. So we thought about integrating some other, when I joined Rowan, to enhance the system and integrating new other inspiration from, dampers, seismic isolation using those concave shapes, and also from nature, where we have this bolt socket connection in our hip joints and also shoulder joints having the cartilage. So can we use 3D printing to actually create bridges that actually can have freedom in geometry to create flaring surfaces that meet the foundation, and after that better distribute the stresses and have another way for energy dissipation rather than internal reinforcement, using either external energy dissipation devices that we developed here at Rowan, or a cartilage type of kind of material similar to the black material here, the damping material between the column and the foundation. So from the old system to the new system, you can see a lot of cracking and partial spalling in the foundation that is actually prohibited by code because it has to remain elastic or damage free. That is mainly because of concentration of the forces as it rocks because of the cylindrical geometry. So what we have schematically developed here is a column that has post tension, will be 3D printed, and post tension to the foundation, and has concave surfaces that allow us to put material that could be acting as a damper and also as external damping system, and that allows us as a rock, instead of having one concentration of a force, it's actually a surface distribution of a force. So here, as you can see, as a rock, it tip on one joint at one point. However, in our system, it would rather have a surface, and this material in between has to be kind of shape memory material using TPUs and other material that can damp the forces. The other one is having initial dissipation from rebar yielding. We move that to the material inside this cavity to allow us to deform and dissipate energy using either HTTP or TPUs and other materials, or external element that activate by rotational friction, by resisting by rotational friction rather than yielding and dissipating or buckling. We did that testing on the small scale device, and we demonstrate at the Lehigh University that we are able to dissipate energy using rotational friction as external elements. So this is what we call the integrated system that we propose. As of now, we can actually also take rid of the external element and tune those cavities and material to damp the desired material. By doing so, we also shifted the system to be seismic isolated, because we actually going to reduce the demand because we get a little bit flexible. So the acceleration will drop, and therefore the demand will be lesser. We are in a phase of testing this idea at Lehigh University in the fall. And we did all the printing requirement, and we are now in the final stage of construction of those columns. So basically, going back to 3D printing, students work on very different designs. So as you can see here, the printing of one of the columns, and that leverage our material ability to create complex shapes and flare in and flare out with high quality and good adhesion between the layers. So this is the end of the socket print. As you can see here, we have an opening in the middle for post tensioning. For this column, we don't have reinforcement, but the idea, as I mentioned, as you isolate the structure, you have lesser demand. So really, we can test the material shear strength and rely on that to resist. However, I'm gonna correct that in a minute. Um, the question would be really no reinforcement, no one would accept it. So go back to the column, how the way we reinforce our bridge columns or general concrete columns is having longitudinal bars and spirals. So, or in bush piece stressing, you will see leaf cavity or duct to do the post-tensioning or pre-tensioning. So our goal here is actually to bring the majority of the column, leave channels or cavities for rebar to be bonded, leave opening for post-tensioning, and for the spiral, we actually try to use an external confinement technique. I know Dr. Nani is well famous on FRB and other work, so there can also be an option to wrap those columns with FRB. So the idea here is to print the majority of the column. Our column is just 6-inch diameter, so basically you'll iterate on the printing process here and print the columns. We did the stop columns to test the capacity of those columns. We did also integration of rebar and robotic casting of those cavity, and we used the Blu-ray material confinement, which is good for impact, and also can give us a benefit for confinement as an external coating. So you can see here we have like 4 columns. One is we tested actually those columns where we have only printed shell, printed grouted, and rebar printed with Relia spray or all. And we did test all those columns also at Lehigh University last winter, and we're able to, as you can see here, to see the mode failures for each of them. So basically, as expected, the 3D printed alone will have brittle failure, similarly to also the reinforced because it doesn't have confinement, and the other ones that has confinement were able to undergo post-peak ductility. Here are the results for those 4 different columns, and you can see here we actually increase the capacity as we add those components, either spray or Proria or the reinforcement, but also we get post-peak ductility. The other project here before we conclude the presentation is related to underwater 3D printing. This was motivated before DARPA project that is announced in 2024. We were actually doing work in this area, but the idea was how can we use water to or other liquid to achieve more slopes as we print. However, now it shifted to be a structure element. So we did the first ever printed underwater was in December or fall 2023. We printed our material underwater and off water. I don't want to spend time here, but you can see clearly the washout of the material as we printed it. During DARPA competition, we did a lot of work to try to demonstrate the ability to do underwater printing. And since then, we make it as a PhD student for Ali, and he took his geopolymer concrete and tried to re-engineer it for underwater 3D printing. We were not winner of the DARPA competition, so we actually get some benefit of not restricted by percentages or certain components. So here's our mix from mix 1 to mix 5 using slag fly, silica fume, different degradation of sand and chemical activator on water. And this is a process we do for underwater. We get our water tank and we fill it with water and we print inside. As I mentioned earlier, the material was initially developed for in-air printing and modified for underwater printing. So as you can see here, the material is actually printed a few cylinder underwater. I know it's not large scale. We are using the tube, but we are also trying to scale that up using the Auger system. And you can see here we achieved like almost 37 layer without noticeable washout. However, we also take it a step and try to create flare destruction in slopes. And as you can see here, We printed also the slope. We have made print some technical issues with the printer, so we have some deformation of the layers. But even with those deformation, the structure was able to withstand, and we're able to print up to 37 layers with 8 millimeter nozzle. One thing I mentioned is like low noticeable washout is we also did work on water quality assessment using pH monitoring and turbidity testing to test both chemical and physical washouts, especially we are using chemical activators. So basically, we'll take material from or water samples from the tank as we print, before printing, mid-print, after print, and every after 6 hours, 18 hours every day for 3 days, and we'll try to do the turbidity test on it to see the physical leaching of the particles. We did also pH testing, started with 7.58 for the tap water and increased to 11.7 because of the alkalinity in the mix. We also did a lot of testing for mechanical testing, compressive strength for the cast version of the material or the printed version of the material, and you can see clearly the decrease of the strength printing underwater. And the goal now is to expand that work for the PhD to include marine sand and other mined element from the ocean, like sediments, and use also seawater as a part of the printing process. And idea is to reduce reliance on transportation of this material in the field. We also we do have work, but still under fitting and revisions. So, in fact, we have one paper published already on in building engineering. If you are interested to know more about this research, I think I am around the clock here. So the last one is a kind of be an open discussion of potential application of 3D printing in infrastructure. We are still in the initial phase of this research for this bio-inspired beam. So in future, hopefully integration of that in precast, and hopefully we're able to verify those beam and enhance the designs. And that could be application for bridges, similar to what we have in the bridge columns. And the idea now for arch bridges, tunnel, underpasses, we all did some work with undergrad students to excite them about 3D printing and come up with different shapes and different existing, notable bridges that they can scale it down themselves and do the modeling and print. For underwater printing, a lot of application, including bridge caissons and others. For retaining and supporting structure, drainage and water system, we do a lot of work on, culvert pipes. And the coastal and marine infrastructure, I know that UM has a lot of work in this area too for coastal restoration. And now we can see how complicated geometry can be achieved with 3D printing. One thing we are very interested in is emergency response, is literally in case of need of social distancing and same time evacuation that would create conflict. So we created a system that can be rapidly deployed using 3D printed and other, commercial material from Home Depot that can be integrated in a wall system that can have two people to assemble temporary shelter with necessary living support. With that, I will try to acknowledge our partners and funding agencies, and I'm happy to receive any. Before I finish, I would like to thank all the students part of this research and lab, and without them, for sure, no result will be presented. If you have any question, please feel free to reach out to me, and I'm happy to receive any question. I think we have a good 20 minutes maybe for questions.